Earth Science class, let's go over Chapter 4, Plate Tectonics. So there was this guy, the scientist Alfred Wegener, and he proposed a hypothesis called continental drift in 1915, really long time ago. And he published a book, The Origin of Continents, where he discussed his hypothesis. And essentially what he was trying to say at the time was that there was a supercontinent called Pangaea, and it began breaking apart about 200 million years ago. And since that time, the continents have drifted from that supercontinent, Pangaea, to their present positions. And the continents did this by breaking through the ocean crust, much like a ship breaking through sea ice. Now, this was a revolutionary idea at the time because up until that point, all scientists, all geologists believed that all land was stationary and had been there for a really long time. So a lot of geologists adopted uniformitarianism. They understood that the Earth was really old, older than we could even conceive. But they figured that the processes that shaped the landscape that we see today is stationary. Like the continents and the outlines of them have remained there forever and are not mobile. Excuse me. You can't really blame them either because, I mean, it's not even really perceivable. Do you feel like right now we're on the North American lithospheric plate? We're moving, about 3 centimeters a year to the west. Do you feel it? Not really. So this is our modern reconstruction of Pangaea. So 200 million years ago, dinosaurs were roaming the Earth at this time. All the major continents were kind of docked together in this major landmass. We call it Pangaea. This is based on all the evidence we've collected to this date, and this is our best reconstruction of what Earth was like 200 million years ago. This is a drawing from Alfred Wegener's book. Alfred Wegener was a German meteorologist, by the way, and through his travels and his study and the collection of his evidence is how he came up with his idea of Pangaea. It's pretty remarkably close to what we have today. And so the way he formulated his hypothesis were through 4 main lines of evidence. The first is the fit of the continents, and specifically here, South America and Africa. And I know you've probably done this before. You've looked at a globe, and you've looked at South America and Africa, and you're like, they kind of look like they used to be together, or they fit together like a puzzle piece or something, right? And it's true. Much later on, an English scientist estimated and included not just the coastlines, but the continental shelves of each continent. And there's about a 92% fit in between these 2 continents along those continental shelves on each of those coastlines. Okay. Another major line of evidence, which we'll talk about in the next slide, are fossils in different geographic areas that match each other. Then there's a similarity between the different rock types in different continents, as well as ancient climates didn't really match up to their present-day locations. Okay, so this had perplexed paleontologists for a while. When they would find fossils of specific species on different continents. The Mesosaurus was a freshwater dinosaur. Couldn't live in the oceans. It just lived in swamps and low-lying areas like that. But you can find fossils of this in South America, but you can also find fossils of this organism in Africa, right? So think about that. How is that possible? How is it possible that a specific species of dinosaur existed on 2 continents that were separated by the entire Atlantic Ocean? That was a very difficult problem for paleontologists to explain. There are a number of explanations I'll show you in the next slide, but they thought perhaps sea level was much lower, and it exposed the kind of land bridge in between the continents, or that they inhabited a bunch of islands in between Africa and South America, so kind of populations kind of moved in that kind of direction and then eventually made it to either South America or Africa. But really there was no good explanation for the existence of the same species, fossil species, on two different continents. And the same goes for the Lithospheric. Okay, this existed in Africa, India, and Antarctica. Okay, and even plant fossils were perplexing because the Glossopteris, this is a fern that lived in very cool climates. And this fern had seeds that were very large and could be only transported by water. They couldn't be picked up by the wind. So really, the spread of this species as a plant species could have only occurred on a single continent by running water. Yet we find fossils of this in Patagonia, South America, Central Africa, Antarctica, right, and in India. If we know the climates of India and Central Africa, they're really hot. Current day, they're found very close to the equator. These are very hot places. So this species could not have existed under those climatic conditions back then. So some paleontologists kind of use explanations to explain how this could have occurred. One is, they rafted. These organisms rafted on floating tree logs, like in the Titanic, except Jack was in the water, I guess. But floated across the Atlantic Ocean and established like an Adam and Eve population in a new continent. That seems highly unlikely. We talked about the Isthmian links lowering sea level, exposing land bridges, but we've mapped the ocean floors. There's no such land bridges between South America and Africa. Here's the island jumping, so populations jumping to different islands, populating them, and then jumping to the next island. These are real explanations. But the islands, there aren't too many islands that would connect South America and Africa, so that Mesosaurus was very unlikely that would have occurred. Or we can talk about continental drift. Okay, perhaps 200 million years ago, Africa and South America were the same continent. It was one major landmass, and the organisms encompassed large areas within that landmass. And about 200 million years ago, a great rift started to form in the middle of that continent and broke it up in two, and they since have drifted to their current positions. So that organism lived and died during the time of that major landmass, Pangaea, was preserved in the fossil record, and then the landmasses split apart and then drifted to their current positions. That was Alfred Wegener's explanation. His next line of evidence was the different rock types and geologic features that you find in different continents. The Caledonian Mountains, the mountains in the British Isles, in Western Africa, Spain and Portugal, and the Appalachian Mountains all have very similar rock types and rock sequences and features. It's almost as if they were formed in the same event or mountain building event, which they were. And so what Alfred Wegener did was not only, kind of fit the continents together like a puzzle piece, but also matched the picture on the puzzle. I'm sure you guys have been doing, maybe some of you have been doing some puzzles during this time of stay-at-home orders and stuff like that. But essentially here, he matched the different mountain ranges together to create a continuous mountain chain. And that's true of today. If we think of the kind of young mountain chains that are being constructed today, like the Himalayas, it's a really long continuous mountain chain, and that's what would have been like a very long time ago. Okay, so that was another line of evidence. And then the last line of evidence were ancient climates. You can look at, as we've learned before, right, sedimentary rocks and deduce what type of environment created those sedimentary rocks. And we can find out what the environment was like in the past, right? And what Alfred Wegener saw is that there are a lot of locations where there are coal outcrops dating back over 200 million years ago in northern Africa, in northern Europe, and in kind of North America, western Pennsylvania type region. And what we know, or what you should know about environments that would eventually create coal is it's typically a swampish, warm tropical climate with the accumulation of a lot of organic matter. Now, would you characterize Northern Europe as a tropical type environment or Western Pennsylvania? No, right? Not as in their current positions. Those environments should be closer to the equator. So what Alfred also did was he moved, so he fit the continents together like a puzzle piece, matched a lot of the rock types from the very old mountain ranges, and then moved known places where there were sedimentary rocks where you could deduce what the climate was like to appropriate latitudes to reflect that. So if you notice, all the coal swamps back then were found closer to the equator, right? So this is where northern Africa was, and northern Europe, and also the coal swamps in the northeast. In addition to that, there are also a lot of evidence of continental glaciers moving through land. Now, when glaciers are really heavy, large, slow-moving rivers, essentially rivers of ice, and they scour the landscape, and they can leave behind big deposits of sediment that eventually become sedimentary rocks, or they leave kind of like grooves in the bedrock, right? And that was occurring in Africa, in South America, and in India. Okay, so how could this be possible, right? How, if the continents were fixed in their locations like they are today, how could we have really warm temperatures here and really cold temperatures near the equator? So what Alfred really did to kind of solve that problem was just move the continents to appropriate latitude. So anywhere that showed evidence of continental glaciation, he moved it towards the southern poles and then matched it up that way. And that's how his map was fairly accurate. Those are his 4 lines of evidence. But his ideas were met with great hostility in the scientific community. It was wild. It was a wild idea. It blew people's minds away, and they rejected his hypothesis. And the main reason, his 4 lines of evidence were sound and strong. However, he could not explain the mechanism that drives the movement of the continents. He incorrectly suggested that they move as a result of the gravitational pull of the sun and moon, and that the continents kind of break through the ocean basins like a ship would break through sea ice. And that's incorrect. And physicists proved him wrong immediately. And so he was kind of laughed out of the community like that. And he passed away before the theory of plate tectonics kind of came about. So it was a shame that he didn't really get to see that his ideas were indeed correct. He just didn't have the right mechanism to explain it. I mean, they're really like, Alfred, what are you doing? What is in your pipe? What are you smoking? Your ideas are crazy. So much later on, following World War II, the theory of plate tectonics kind of took hold. And what happened here was after World War II, we had a lot of ships out at sea, no longer fighting a war. They were equipped with a lot of new technology. Oceanographers started to explore the seafloor because the seafloor had long been a complete mystery. People just assumed it was just a vast nothingness of flat, wrecked ships and sediment. But when they mapped the ocean floor, they were surprised to find that there's an entire mountain chain down there and a lot of volcanic activity. We call this the ocean ridge system, and it winds through all the major oceans. Another crazy discovery that occurred during that time was that we could start dating rocks through radioactivity. And they found that ocean crust they collected was not older than about 180 million years. And that really perplexed scientists for a long time, because the oldest rocks on the continents are about 3.8, 3.5 billion years old. So they were expecting the ocean rock to be about the same age, right? But they found that the oldest ocean crust was only 180 million years old. So they wondered, like, what had happened to all the ocean crust from that was older than 200 million years old? Like, what about 1 billion year old ocean crust? Where is that? Where did that go? How come it's not present, right? And then they also noticed that there was a lot less sediment accumulating in the deep oceans than they had previously calculated. And they wondered, where did all the sediment go? Like, how come in certain areas of the ocean there's very little sediment, and other areas there's much more sediment? So these kind of discoveries led to the development of the theory of plate tectonics. And essentially what the theory of plate tectonics states is that we're surfing on lithospheric plates. We are living on top of a rigid lithosphere, and that sits on top of the asthenosphere. Okay, so the lithosphere, which is this right here, from here to here, is composed of continental crust or ocean crust. So here's the ocean crust, here's the continental crust, and a portion of the upper mantle. Okay, and the reason why it's called the lithosphere is because it's a strong outer layer that behaves rigidly. Okay, so it breaks. So like if you grab a pencil and start bending it, eventually it'll snap. That's rigid behavior. Okay, and so when those events occur, when they're snapping along movement of the lithospheric plates, you get earthquakes. Then below that lithospheric layer, exclusively in the mantle, we have the asthenosphere. And here in the asthenosphere, temperatures continue to rise as you go deeper and deeper. And the rocks here in the upper portion of the mantle, in the asthenosphere, they're very close to their melting temperatures, which makes those rocks very weak and capable of flow. So they're kind of like plasticky. Like if you apply stress to it, it's going to kind of move along with that stress. So essentially, because of those differences in the way these two materials behave, they're essentially separated from one another. So they're detached, essentially. So the lithospheric plates can move independently of the asthenosphere, okay, or can move along with it. All right, so they move separately. So this is an image of our globe with the lithospheric plates kind of separated out. So we have the African, Eurasian, North American, South American. There's a smaller Caribbean plate here, an ocean plate, a Cocos plate over here, the Nazca plate, which is an ocean plate. And if you notice, these tectonic plates can both have continental crust and some ocean crust attached to it. Some of them are just portions of ocean crust. Okay. I think there are 12 major tectonic plates. Okay, you can see them here. Here's a flat version of the globe. And then, so each of these plates, they kind of interact with one another. They're moving, right? So they're drifting in certain directions. And so that leads to is plate-on-plate action or interaction. And there's 3 different types of plate boundaries where the majority of geologic phenomenon occur. There's a divergent plate boundary. This is where you have 2 plates moving apart from each other. Okay, that's anywhere in red. Okay, so you can see there's divergent plate boundaries all along the ocean floor. There are convergent plate boundaries. This is where 2 plates crash into each other. Those boundaries are in blue, so you can see them here on the west coast of South America, through Central America, Pacific Northwest, all along the Pacific Plate. All these areas are where plates are kind of crashing into one another. And then there are transform plate boundaries, and this is where 2 plates kind of move side by side. They're not moving away from each other or against each other. They're just gliding past each other. And gliding's a terrible term. They're really grinding past each other. All right, so let's talk about divergent plate boundaries. We often refer to them as constructive margins, and that's because new ocean crust is being created here. Okay, 2 plates are moving apart from each other. And when that happens, the asthenospheric mantle kind of upwells or moves up to lower and lower pressures or closer to the surface, and that causes melting. Okay, so this creates ocean ridges. Okay, and also what we refer to as seafloor spreading. That's the process where you generate new ocean crust. So when you have a divergent plate boundary, you have ocean ridges that develop. These huge mountain chains that exist at the bottom of the ocean. And along those ridges, at the center of the ridge, there's typically a valley where the volcanism occurs. And the volcanism that occurs there is what creates new seafloor. Okay. You can also have divergent plate boundaries on continents. So we'll talk about that in a second. So here you go. Here is a divergent plate boundary, a mid-ocean ridge in the middle of the Atlantic Ocean. We call this the Mid-Atlantic Ridge. So remember here, this is the flat abyssal plain, and then here it kind of rises up like a mountain, higher elevations, and then there's this kind of central rift valley where it drops down a little bit lower, and then there's these high rift valleys again over here. So what's going on here is that this plate is moving in this direction, this plate is moving in that direction, and it's diverging, okay, moving apart. And so to fill that gap, a lot of the asthenospheric mantle moves upwards, decompresses, melts, and those melts rise up through this kind of new space here. A lot of the melts kind of inject themselves and become part of the ocean crust, crystallize deep underground as intrusive igneous rocks. But some of them do erupt on the surface and erupt at the bottom of the ocean floor. Think of it like this. Imagine, when you ride your skateboard or bike or whatever it is, and you fall down and you scrape your knee or your elbow and you start bleeding, you'll start forming a scab, right? And this, I know this is a pretty gross analogy, but it makes sense, trust me. Imagine you have a scab, and imagine you start spreading your skin open where the scab is. What's going to come out? Blood, right? Blood's going to start coming out, and then it eventually will dry and become part of the scab. Okay, so you see it now. This is kind of like earth skin diverging or ripping apart, and then magma or earth blood coming up. Okay, I've lost the crowd. Okay, let's move on. But that's essentially what's going on here. So these mid-ocean ridges are everywhere. They wind the world's oceans. They cover about 22% of the Earth's surface. So here's the Mid-Atlantic Ridge. Okay, here's the East Pacific Rise in the Pacific Ocean. And they go all the way into the Indian Ocean. So we've got a lot of it. Iceland's a pretty cool place because Iceland is an island in the Atlantic Ocean, but it's also a hotspot. A hotspot's an area where there's unusual, anomalously high temperatures in the mantle, which creates a mantle plume, and that creates a lot of voluminous volcanic eruptions. And if you have enough volcanic eruptions at the bottom of the sea floor, all those eruptions and flows will pile up on top of each other, and then you'll get land. And that's essentially what Iceland is. And Iceland, the island itself, is kind of split between two tectonic plates, the Eurasian plate and the North American plate. Okay, and then the Rift Valley kind of goes right through the center of the island. And no big surprise, there are a lot of active volcanoes in Iceland, and a lot of these volcanoes are found in this Rift Valley. Okay, so Iceland's a cool place to go so you can actually see the processes that occur at a divergent plate boundary. Okay, here's the Thingvellir National Park. Here's the valley right here. So here's the valley in between the two tectonic plates, and here's the kind of like the ridge on one side of that valley. So you can kind of cross the valley and go between two tectonic plates, the North American plate and the Eurasian plate. Okay, here is a waterfall with, these are volcanic rocks called basalt, an extrusive igneous rock. These are called basaltic dikes. So these are like injections of magma as they're moving towards the surface. So this is what we would see in ocean crust just below all the sea sediment. We would see a lot of this basaltic magma trying to make it to the surface through these injections and then solidifying into basalt. All right, and Iceland's pretty amazing too because instead of drive-through theaters, they have drive-through volcano falls. You can just watch lava flows as they kind of come down a crater and slowly solidify in certain areas. Look, these are cars, just to get some perspective of scale. So you can come out here and watch some volcanic activity, which is kind of nice. Okay, so divergent plate boundaries can also be found on continents, not just at the bottom of the ocean floor. When it occurs on continents, we call it a continental rift. And what will happen here is the landmass will just split into two or more segments. So initially what you have is an elongated depression that will form, and then the crust in that area will start to sink. And as it continues to sink and the depression lengthens, oftentimes a really narrow sea will come in and invade the low-lying area, and you start creating a new ocean basin. And where that's happening today is the East African Rift. Okay, so this is the entire process over many millions of years of geologic time. This will occur. You have upwelling of the mantle that thins the overlying continental crust. You have initial upwarping, so you actually kind of push the crust upwards, but then the plates start to move away from each other. Okay, and when that happens, then you form this rift valley, and you have a very low-lying area. The volcanoes will start to pop up in the rift valley. So this is East Africa right now. Oh God. Okay. And then as that depression lengthens and becomes lower and lower, ocean water can invade in, and you get a linear sea. And then over time, as these plates continue to move apart from each other, the ocean becomes larger and larger, and you get the development of a mid-ocean ridge. And then here's the birth of an ocean basin. Okay. So here's the East African Rift. If we're going back to the skin analogy, Earth skin analogy, these are stretch marks on the Earth's surface. Okay, you guys still with me? So here we go. Here's part of, I guess, what is present-day Somalia, kind of moving in this direction. Here's the rift. So these are those stretch marks. These are those rift valleys. Okay, and perhaps they'll maybe connect down this way. Maybe it'll go this way. It's kind of hard to tell. But essentially, this portion of East Africa is going to rift off into the Indian Ocean, and we'll have Madagascar 2.0 in kind of millions of years from now if this continues. And if it continues, a narrow sea will form in this area. Okay, where a narrow sea is formed as a result of divergence is the Red Sea. And if you see here, this is the Red Sea. See how it's a kind of narrow sea? The Arabian Peninsula was once part of Africa and has since split away and is forming a mid-ocean ridge here. So you can kind of see the step-by-step evolution of a divergent plate boundary. Okay, let's talk about convergent plate boundaries. Convergent plate boundaries are referred to as destructive margins, and this is where you have two tectonic plates kind of crashing into one another. And when this occurs, most of the time, one plate will slide beneath the other plate, and we call that subduction. Okay, so subduction zones are areas where a lithosphere descends into the mantle. And when this occurs, when you have lithosphere descending into the mantle, that creates deep ocean trenches. And deep ocean trenches are kind of arc-shaped, sometimes linear-shaped, deep gashes on the ocean floor, and they're the deepest parts of our oceans. Here are some examples: the Peru-Chile Trench, the Marianas Trench, which is the deepest part of the ocean floor in the world, and the Tonga Trench, okay, in the Southwest Pacific. So there are a number of different situations. So let's talk about when ocean crust and continental crust kind of converge on one another. Ocean crust is made of basalt, and basalt is denser than the typical continental crustal rock like granite. It has higher density. So what will happen is the denser ocean slab will sink into the mantle as these two things collide. And the continental block is very buoyant, so it kind of just floats on top. And as the ocean crust kind of descends into the mantle and sinks because it's so heavy from its density, right at about a depth of 100 kilometers, the water from the kind of hydrothermal altered ocean crust will start to kind of de-water and come off of the surface of the ocean crust, and that introduces a lot of water into the stenospheric mantle, and that lowers the mantle temperature, and that creates melts. And so those melts will then start to buoyantly rise through the mantle, and then underneath, they kind of pond underneath the overlying continental crust, and a lot of them actually make their way through the continental crust and can erupt at the surface, and that's why we have volcanoes in these types of geologic settings. Okay, one example here, the Pacific Northwest. If you've been to Washington or Oregon, they have active volcanoes. There's Mount Hood, Mount Adams, Mount Rainier, Mount St. Helens. Okay, these are all volcanoes that are part of this continental volcanic arc. And what's occurring here is the Juan de Fuca plate, which is an ocean plate, is subducting, sliding underneath the continental crust. And as it does this, there's dewatering, melts are generated in the mantle, and most of those melts kind of move through the continental crust and stagnate, crystallize as intrusive igneous rocks, but some of them will make it to the surface and erupt at volcanoes like you see here. This is Mount Hood. So this is ocean and continental convergence. We can also have ocean-ocean convergence, or two ocean plates kind of crashing into each other. When this occurs, one will descend underneath the other, and it's typically the denser ocean plate, which means it's typically the older ocean plate. It's colder, it's older, it's more dense. That'll sink into the mantle. And when this occurs, you get subduction again. And you have the generation of magmas in the mantle asthenosphere. And this time you get volcanoes that will pop up on the overlying ocean crust, and you'll create a volcanic island arc. Okay, so some examples of this are the Aleutian Islands. That's in, kind of off the coast of Venezuela, that curve upwards into the Caribbean. The Marianas Islands, Japan, okay, are some examples. So here are the Aleutian Islands. Here we have the Pacific plate is moving here and is subducting under this portion of the ocean crust over here. So then you start generating these volcanic islands as a result. So here is that ocean trench, deep part of the Pacific Ocean, and you get volcanoes that rise from the bottom of the ocean crust and come up as islands. So that's a volcanic island arc. Okay, and then there are there's continental convergence. This is where if you have two lithospheric plates that kind of run out of ocean crust, so they'll no longer subduct because it's continental crust on continental crust action. They're both not very dense. So what ends up happening is kind of like two cars crashing into each other, and they're a head-on collision, and their hoods kind of crumple upwards. And when that happens, you start creating mountains, or that's how mountains are generated. So a really cool example of this is how the Himalayas formed. India was kind of like its own island continent in the Indian Ocean, and 71 million years ago it was moving kind of northward, and initially it had a leading edge of ocean crust which was subducting underneath the Eurasian continental crust, which created a continental volcanic arc here. But eventually it kind of ran out of ocean crust. So then what happened was all this continental crust started to collide with all this continental crust. And there's no subduction. Really, the Indian plate kind of gets pushed underneath the Eurasian plate, but it doesn't subduct into the mantle. It just kind of gets pushed underneath and moves in this direction, continued. And as a result of that, it basically shortens the crust on either side and pushes all of these rocks upwards. And that's why we have the majestic Himalayas today, because of this process. They're still growing today. So this collision began about 50 million years ago, and it's producing the amazing Himalayan mountains. This is Zermatt, by the way. This is in the Alps. So it's the same process. Continental crust kind of colliding with continental crust produces beautiful mountains like we see in Switzerland. Okay, then there are transform plate boundaries, and this is where two tectonic plates slide past one another. So they're not colliding into one another, they're not moving away from each other. They're moving side by side, okay, grinding past each other like you see in this GIF here. So no crust is created or destroyed, okay. Most of them occur in the ocean floor, okay, and they help accommodate movement of two spreading centers. So this line red here is a spreading center, so the Juan de Fuca plate's moving in this direction, the Pacific plate is moving in that direction. Here's the mid-ocean ridge. But in between those spreading centers, we lived on a curved surface, right? The Earth is curved, right? So you can't have a straight line on a curved surface, so these spreading centers are going to be offset. And then they're offset, and their movement is accommodated by these transform boundaries, like right here. This is one. Here's another one. Here's another one. Okay. And you can have transform boundaries on land. The most famous one is the San Andreas Fault right here. This boundary helps accommodate movement from the Pacific Plate and the North American Plate. So the Pacific Plate is moving in this direction relative to the North American Plate, and then that creates essentially earthquakes all along this fault here. Like eventually Baja California and a large part of Southern California, including Los Angeles, will be kind of ripped off and sheared into the ocean and become like a linear island. Again, though, millions of years from now. Here's an example of the San Andreas Fault. This is Wallace Creek. It's a creek that kind of runs close to the fault, and it used to run down in this direction, but because of the plate motion, now the river runs along the San Andreas Fault and down its original course, and it keeps changing because of the plate motion, which is incredible. Okay, so even though the Earth's total surface area doesn't really change in size, or the shape of the plates are what are changing. Okay, the plate boundaries migrate, and plate boundaries can be created or destroyed. And that's what's kind of so amazing about the theory of plate tectonics, is that all of a sudden it started to explain all the geologic phenomena that we see, and also the kind of evolution of landscapes. You know, geologists always wondered why there were volcanoes in the Pacific Northwest and Central America, in West Coast South America. Like, why? Why not on the East Coast in Brazil? Why aren't there volcanoes on the East Coast of Brazil, right? Why are there mountains in the Himalayas? How did the Himalayan mountains form, right? Why is there all of a sudden this mountain chain at the bottom of the ocean? All of these questions can be answered by the theory of plate tectonics. Why there are volcanoes on the Pacific Northwest? Well, because there's subduction. There's subduction there, there's subduction in Central America, there's subduction in South America. Why are the Himalayas continuing to grow today, and why is there a huge mountain chain there? Well, it's because of two tectonic plates kind of crashing into one another. Why is Japan a volcanic island with active volcanism? Well, there's subduction there, and there's a convergent plate boundary. So a lot of the geologic phenomenon that occurs can all be tied together to the theory of plate tectonics. That's why it was so important. It really was like a paradigm shift in the sciences when we started collecting all that data. Okay. So back to Pangaea. Woo, tangent there. Okay, so Pangaea began to break up about 200 million years ago. And what that did, remember, if you start forming a continental rift, you'll have a little low-lying valley, then a narrow sea, then a full-blown ocean basin, and voila, you have the formation of the Atlantic Ocean basin. So you can call the Atlantic Ocean, its age is about 200 million years old. That's when it formed, okay? And when Pangaea broke up, then India kind of collided into Asia and started forming the Himalayan mountains. Those are two major occurrences after the breakup of Pangaea. Here's the best reconstruction of what has happened since the breakup of Pangaea. This is where we were at 200 million years ago. Over the course of 50 million years, we had a narrow sea form between Africa and North America. India kind of broke off of Africa. Okay. Then over the course of the next 60 million years, South America and Africa broke up. India broke off of, or Madagascar broke off of a piece of India and Africa. Australia began to kind of move northward. Okay. Antarctica kind of continued to move southward over the next 30 million years. Rifts started to, India began to move northward. North and South America weren't quite connected yet. Atlantic Ocean basin continued to grow. Over the past 20 million years, India docked itself into Eurasia, starting to create the Himalayan mountains. Rifts began to start forming in between the African continent and the Arabian Peninsula. Antarctica kind of moved further into the southern pole and became isolated and then completely covered in ice. The ocean circulation changed, and no more warm tropical waters were making it to Antarctica, so it became frozen over. And then here we are. This is where we are today. Okay, so up until this point, I've just been kind of like the theory of plate tectonics. Yeah, but where's the evidence to support this? You guys need to know this, right? So a lot of the evidence that kind of came trickling in after World War II was from ocean drilling. Okay, This was some of the most convincing evidence that confirmed seafloor spreading and therefore kind of lithospheric plates moving. Okay, one was taking a look at the age of deep ocean sediments. We found out that they're very young, and also kind of the age progression. Okay, I'll show you that in a second. And the thickness of the ocean sediment and the seafloor. Okay, so what we found was we scientists took out ships like this, and they drilled down into the ocean crust, collected the sediment, collected the basaltic rock, age dated that stuff, and what they found was the youngest ocean floor was found at these peculiar mountain ranges, these rift valleys right here. And then the older ocean crust was found further away from these rift valleys. In addition to that, the thickness of sediment also increased when you moved away from the center of the ridge. Okay, and it increased in both directions. So that was initially perplexing, right? And so what they realized is that, yeah, so perhaps the plates are moving in this direction. They're spreading apart. New ocean crust is being created. That's why there's no sediment on top of it, because it hasn't been around long enough to have sediment accumulate over it. And the oldest ocean crust is all the way over here. And they've been around for long enough to have sediment accumulate on top of it. Then there were hot spots and mantle plumes that helped provide some evidence for moving lithospheric plates. So a hot spot, much like Iceland, okay, there are other hot spots like Hawaii. And they are formed from these mantle plumes. These are kind of really long-lived structures that are really hot and move through the mantle as these like diapirs, these huge diapirs. And as they rise, they begin to partially melt, and all these melts kind of, once they get close to the surface, a lot of volume of magma is generated, and it moves through the lithospheric plates and erupts at the surface. Okay. So when that occurs, you have a rising mantle plume. A lot of melts are generated. Those melts rise up and erupt on the ocean floor. And if enough of this erupts on the ocean floor, then you'll have a volcanic island. And there you go. You have Hawaii. Hawaii is an active volcanic island. Kilauea, Mauna Loa and Kilauea are both active here on the island, and they're constantly erupting. Some of that stuff makes it all the way to the ocean. It's pretty amazing. And what they find out in the big island of Hawaii is these are the youngest rocks in Hawaii. All the other islands, Maui, Molokai, Oahu, and Kauai, there's no more volcanic activity. Okay, and what they see too is an age progression. Youngest rocks are found on the big island where most volcanic activity occurs, and then as you go in this direction, the rocks get older. And Kauai has the oldest rocks, 5.6 million years old. And if you continue to go in this direction and map the ocean floor, you start to find that there are seamounts, which are ancient volcanoes that have since eroded away from the ocean, littering the ocean floor. And then there's a kink in it here. And what that essentially means is that the Pacific plate is moving in this direction, right? So it's moving in this direction, and the hot spot, which is right here, remains fixed. So as the plate moves in this direction, an island that was once active is going to move away from the hot spot and then become kind of extinct, right? And then a new island will surface over here, a younger island with more activity, okay? And then what happens to these islands is eventually they just slowly erode away and fall beneath the surface of the ocean to become seamounts. And so the next Hawaiian island will likely form over here. In a couple million years, there'll be a new island. And so what that indicates is that the plate is moving in this direction, and we can follow the seamounts and find out that the plates have, first of all, that they're moving, and second of all, that their direction of change in the past, like they've moved in this direction, kind of like in a northwest direction, and in this direction, in a north direction, about from 80 million years to about 48 million years. That's the direction of the movement of the Pacific plate. And so there are a lot of hot spots on Earth. The Galapagos Islands are a hot spot. Azores are a hot spot. And so we can go to each one of these places and map out those seamounts, and that'll show us the direction of plate movement. And lo and behold, all the hot spots on the Pacific plate show the same movement, okay, and all the other plates. So you can plot the tracks of these hot spots to kind of delineate or show the movement of the plates in geologic history over hundreds of millions of years. Okay, then the next major line of evidence was through paleomagnetism. All right, so basaltic rocks are volcanic rocks, and they contain a mineral called magnetite. And magnetite is magnetic. It's iron rich, so it's influenced by our Earth's magnetic field. Remember, our magnetic field is generated by the core of our Earth, the outer core, which is in motion, and it creates those magnetic field lines. Okay, so when basalt erupts, right, what happens is as it cools and the minerals begin to crystallize, the magnetite minerals become magnetized, and they kind of like a compass needle, they point and align with the magnetic field that exists at the time of crystallization. Okay, so the magnetite essentially crystallizes and freezes in place, in position, and that helps scientists determine the location of the North Pole. And so we refer to this as paleomagnetism because now what scientists can do is they can look at past eruptions from volcanoes that occurred maybe 10 million years ago, 20 million years ago, and look at those magnetite grains from those eruptions and determine what our magnetic fields were like in the past. And then you can reconstruct and create a paleomagnetic timeline of our Earth. And so that's what paleomagnetism is. And what they found was, and it's true today, our magnetic North Pole is not the same as our geographic North Pole. And our magnetic North Pole kind of moves with time. Google Maps has to update and adjust for this movement. Okay, so like when you hold the compass and the needle points north, that's not pointing towards the geographic north where the axis perfectly goes through the sphere of our Earth. It points towards the magnetic North Pole, which is somewhere kind of in Canada, in northern Canada. And so that changes over time. And there are real big drastic changes over geologic time. So when scientists started to collect data on the location of the magnetic North Pole, assuming that the continents didn't move, they plotted that data. So everything here in green was the location of the magnetic North Pole from lava flows going back 500 million years. So here's today's location of the magnetic North Pole. 100 million years ago was here, then here, then here, then here, then here. Well, then they did the same thing with lava flows in North America, but the problem was with the same ages, right? So 100 million years ago, in the perspective of North America, the North Pole was here, and then here, and then here, and then here, and then here. That presented a huge problem because you can't have two magnetic North Poles. So the problem was they were assuming that the continents were fixed. And if they adjusted for the motion of the continents, like, hey, 100 million years ago, North America and Eurasia were actually kind of over here, then what they noticed, see here on this image, they adjusted for the motion of the lithospheric plates, and now the magnetic North Poles match or more closely. Okay, and so this line of evidence was called polar wandering paths, and that kind of essentially suggested that the continents had been in different positions in the past due to paleomagnetism. Another crazy thing that our Earth does are magnetic reversals. Okay, so over periods of hundreds of thousands of years, every once in a while, the Earth's magnetic field reverses polarity. What that means is, say you're holding a compass and the needle points north. So if there's a magnetic reversal, the needle will start to point south. You're like, what? What's going on here? That's the magnetic reversal. So the North Pole becomes the South Pole and vice versa. So what happens here is if the rocks that exhibit the same magnetism as today's magnetic field, we call that normal polarity. And then the rocks that exhibit the opposite of today's magnetic field, we call that reverse polarity. And so once they developed this concept, we started to create the magnetic timescale. So with seafloor spreading, okay, so say here you have rising asthenospheric mantle, new ocean plates being created and being kind of diverging, right, and new ocean crust and volcanism occurring right at this rift valley. These eruptions here, this is going to be basalt that's going to crystallize, and then it's going to reflect the polarity conditions at this time. And in this case, they're all white here, just whatever color, it doesn't matter, that reflects normal polarity. Okay, but plate creation continues, right? You keep going, but at some random time, there's a polarity switch, right? So the magnetic fields change, and now all the new ocean crust that's being generated is going to reflect that change in polarity. And so all of these new rocks that are being created are all those magnetite minerals are going to be pointing towards the other pole. Okay, and if the polarity changes again, the new ocean crust that's being created at this time will show the normal polarity. And so what you get is kind of like a barcode symmetrical pattern on either side of the mid-ocean ridge, where you have reverse, normal, reverse, normal, normal, reverse, normal, reverse, repeating itself like a mirror image right through the center of this rift valley. And that was really the smoking gun that helped prove seafloor spreading. Remember, they're on boats. People are on boats, and they're mapping the ocean floor. It's not like you can see it actively move. It's only moving a couple centimeters a year, so you can't be like, oh, gotcha, you moved. I proved that you move, right? So you had to use this kind of data to show that in geologic time, this has actually moved long distances. So this is real data that was collected off the Pacific Northwest in the late 50s and early 60s. So they towed a magnetometer off the end of the boat to collect the paleomagnetic data on the sea floor, and specifically across a seafloor spreading center. Here's that data, and this is the spreading center. So on either side of the spreading center, you can see the same symmetrical pattern: normal, reverse, normal for a very short period of time, reverse, normal, reverse. Then over here you see normal, reverse, normal for a very short period of time, reverse, normal, back and forth. And that essentially was the smoking gun to prove that, yeah, new ocean crust is generated here, and these plates are moving away from each other. So that was a direct line of evidence that helped substantiate the theory of plate tectonics. Now, a little hint here, you're probably going to have to recall different lines of evidence to both prove the theory of plate tectonics and also the hypothesis that Alfred Wegener proposed of continental drift. Little tidbit, gold nugget for you guys that are actually listening to my lecture online. Okay, and then the last line of evidence really is heat flow on the sea floor. Okay, if you can measure how much heat is kind of radiating off the crust of the Earth, and a lot of heat is coming through those mid-ocean ridges, which makes sense because this is where the majority of volcanic activity occurs on Earth, in these kind of divergent plate boundaries. And then in other areas, it's not much heat is kind of dissipating through the crust. Okay, so how do we measure plate motion? Well, what you can do is, if you know the date or how old the ocean crust is, and then the distance they are from where they were created, like here, this is the youngest ocean crust. Over here is the oldest ocean crust. So if you know how old this ocean crust is, you just find out the distance from here to here, right? Motion is like a rate of distance divided by time. So you can use that data to find out how fast these plates are moving. And essentially, it's a couple centimeters a year. Okay. We can also use GPS measurements to find out how quickly the plates are moving. This is very accurate down to the millimeter. Okay. So the North American plate, for example, is between 2 and 3 centimeters a year, moving in that direction. Okay. Some ocean plates are moving fairly quickly. The East Pacific Rise is creating new ocean plates at about 15 or 16 centimeters a year. The Nazca plate is moving between 5 and 7 centimeters a year. So it varies a little bit, but it's essentially centimeters per year, or tens of centimeters per year. So what drives plate motion? This is what Alfred Wegener kind of couldn't explain at the time when he was presenting his continental drift hypothesis. And researchers today agree that convection in the mantle, motion in the mantle, is the driver of plate tectonics. And there's two specific forces that that drive plate motion. One is slab pull, and the other is ridge push. Okay. Convection is essentially kind of motion of particles in a medium because of heat. So the best example of this is boiling water. Here's your stove. It's really hot. It's heating up the water here, lowering its density so it rises, and then as it rises it cools down, and then its density increases, and then it sinks, and then creates these circular convection cells. And so scientists believe that's how the mantle moves. It creates these convection cells, and heat is dissipating off the core, which kind of convects through the mantle. Okay. Here are those specific forces. This is ridge push. Remember, here's a very low-lying area of the ocean floor, and as you go up in this direction, you're going up to higher and higher elevations. Okay, the reason why it's higher is because all this heat from magmas that are being generated kind of pushes the ocean crust upwards. So all that kind of heavy and that force of gravity kind of pushes the ridges downward, and that forces the plates to kind of move away from each other. And as the plate cools down, then it runs into a convergent boundary. It then sinks, and this is called the slab pull force. Like the slab here is sinking, and it's pulling the rest of the ocean plate along with it. It's kind of like pretend you, me, and Andre the Giant are all tied together, tethered to a rope. And if you don't know who Andre the Giant is, it's incredible. He's huge, massive man. He's like heavier than Shaq. Had a crazy drinking problem. Anyways, if we were standing on the cliff of the Grand Canyon and Andre the Giant falls off that and we're tied to him by a rope, we're falling with him. Okay, that's the slab pull force. The ocean crust is so dense, it's just pulling everything down along with it. So those are the specific forces that kind of drive plate motion. And then scientists have kind of agreed there's two kind of explanations, there are two models to explain plate motion. There's the Whole-Mantle Convection and the layer cake model. Let me show you what they look like, the last two slides. Here, this is the Whole-Mantle Convection, so heat is dissipated from the core, and this heat kind of forces convection in a whole and create these large convection cells with hot rising mantle plumes, right? And this is what drives plate motion at the surface. You can also have huge rising diapirs, hot spots derived from the mantle. Then here's subduction. You can see that subducting plates kind of stagnate here, and then they break apart, and they actually kind of make it to the core mantle boundary. Okay, so here, the Whole-Mantle Convection, you have huge circular whole mantle movement that's transferring heat. In the layer cake model, you have faster flow near the surface. So here's kind of like an upper convection cell, okay? And then closer to the core, you have convection, but it's much slower. We call that sluggish flow. So these are the two competing ideas on why or what drives plate motion on the surface: Whole-Mantle Convection or this layer cake model.